So with each of these, something I'm going to try first is direct substitution, which is taking that value that x is approaching and plugging it in. And the idea is if it comes out to a defined value, we're done. We're just getting the y coordinate of our function at that point, which is what the limit ends up being. So we're going to try plugging in first, but we're also going to look at our scenarios where what if that doesn't work? What if that makes our function undefined? What if it's not going to the right value for the limit? And with that, we can use some algebra rules. So if you can, I'm separating this up into 3 parts because I want to get lots of good review of those properties that we can use for simplifying our functions. But a good idea would be to pause this, try out this part 1, part 2, part 3 on your own of that. Try just plugging in the value for x first and simplifying. And if it doesn't work, try to think of some ideas first of how it would simplify. And then you could use this video as a way of checking your answers or getting a review of those methods that you might need. Okay, so let's go ahead and jump in. So this first one, we have a nice polynomial. We're looking as x approaches -2. So direct substitution, what I'm going to try to do is just plug in 3 times -2 squared minus 5 times -2 plus 4. And I shouldn't run into any issues here. There isn't a chance of this function being undefined or does not exist or anything like that. So we're getting a 3 times 4 plus 10 plus 4. So 12 times 10 is 22 plus 4 is 26. And that would be our limit. Okay, no issues there. Just plug it in and simplify. Okay. Here, seeing this rational function, what I want to be careful of is if the denominator becomes 0. So what I'm going to do is just to the side kind of plug in what happens when I plug in 4 into the denominator. Well, I'm going to have 16 minus 28 plus 12, which is going to be a -12 plus 12, which is going to turn into 0, and that is no good. So this is where we're going to need to simplify this in a way so that I can plug in +4. So with a scenario like this, what we're going to do is we're still evaluating our limit as x approaches 4, so I need to keep that notation there. There isn't really anything I can do with the numerator, but what I can do is factor the denominator. So 2 values that multiply to 12 but add up to -7, that should be a -3 and a -4. And what this is showing me is that in terms of a rational function, this is actually creating a hole at x equals 4. If I graphed this, I would be seeing maybe something like this at x equals 4. So what that happens is if I try to plug in 4, it's undefined. But what we can do is in simplifying the rational function and kind of it's not removing the hole because the hole is part of the function. But what we could do is see what happens if the function is defined at 4 by canceling out that common factor and having just 1 over x minus 3. If we graph 1 over x minus 3, it graphs the same exact function, but it closes the hole. And then we can get an idea of what that y coordinate is by plugging in x equals 4. So now I'm going to get rid of my limit notation because I'm plugging in 4. And now I can evaluate it as 1 over 1. So it's just a value of 1. So if you have a rational function where the denominator is turning into 0, try factoring and canceling to get to a point where you can plug in that value for x. Okay, in this case here, I'm going to try to plug in 5, and my only worry would be if this comes out to be negative underneath. So I'm going to have my square root, 5 squared minus 5 minus 20. So a 25 minus 5 minus 20. So this is just going to be square root of 0, which is defined as 0. So we're all good there. With this next one, excuse me, what we're going to have is if I try to plug in 5, it's not going to be good for that denominator. I'm going to end up with a denominator of 0, which I don't want. With this one, I even provided a graph so that you could see when I'm at x equals 5, we're graphing a hole. But what we could see is because we have the graph, we can see we should be getting a limit of 3 out. But what I want to be able to do is prove that algebraically. So to prove it algebraically, what we're going to do is what we did up above with factoring and seeing if we can get some things to cancel out so we can see the function and how it would graph if we plugged the hole. So multiplying to -20 but adding up to a -1, we're going to have a t minus 5 and a t plus 4. And we still have t minus 5 in the denominator, but now we can see where that value that's creating the hole cancels out. So really what we're doing is evaluating the limit as t approaches 5 of the square root of t plus 4. So now we can go ahead and plug in 5. So we have a 5 plus 4, which is the square root of 9, which is giving us that value of 3, which we could see in the graph itself, but now we proved it algebraically. You know what? Let's go ahead and keep going on to the next part. I was going to see how long these ended up being, but I think we can kind of squish this together a bit. Okay, our next one here. So if I try to plug in 0, we're going to run into issues with the denominator there. So, but we don't have anything to factor because we don't have a quadratic anywhere, so we can't use that. So instead what I want to do is I'm looking at that numerator. And something we can do when we have this mixture of radical and constant is we can multiply. I'm trying to remember the terminology. The conjugate. It came back to me as soon as I paused the video for my recording. We're going to multiply by the conjugate. What we're basically doing is creating the difference of squares. And what that'll let us do is let's get rid of that radical, and then maybe we can start canceling things out. Because at this stage, we can't cancel out those h values because one's trapped under the radical and one isn't. So the trick we're going to use here is we're going to multiply by the conjugate. Let's go ahead and write that up here so you can look it up if you need to. And whatever we multiply the numerator by, we also have to multiply the denominator by the same thing because we can only be multiplying by values of 1. So I'm looking at the numerator here because that has the radical. And what we do is with the conjugate, we're multiplying by, we keep that 1 plus h. We keep that 1, but now instead of subtraction between them, we're going to have addition. And we're going to have the same thing in the denominator. So when we do that, so I'm still evaluating the limit as h approaches 0. We haven't evaluated the limit yet. But when we start foiling here, what should happen is we'd get the difference of squares out. So essentially, we're going to have this square root of 1 plus h, that being squared minus 1 being squared. And then the denominator, we're just going to have this h times root 1 plus h plus 1 multiplying together. I'm going to go ahead and leave them separated like that. Okay. So in the numerator, if I take care of those squares, so I'm still evaluating the limit as h approaches 0, 1 plus h squared is just going to be 1 plus h, minus 1 squared, which is just 1. Again, keeping this h times root 1 plus h plus 1. So in the numerator, we're going to have limit as h approaches 0 of just h over h times root 1 plus h plus 1. And I'm continuing on because if I still try to plug in 0 at this stage, we're running into issues in the denominator. We're still getting a denominator of 0. But at this point, what we're going to get is a cancellation of h values. So now what I can do is I'll have the limit as h approaches 0 of 1 over root 1 plus h plus 1, and now I can plug in 0. So now I can finish evaluating the limit of 1 over root 1 plus 0 plus 1, which would be a 1 plus 1 in that denominator, so we're getting out a 1/2. So a little algebra review there of if we want to get rid of our radicals, what we can do is multiply by the conjugate, and that'll help us. I mean, we still have radicals, but it lets us do something kind of creative, if you will, so that we can cancel things. And we're basically working with it until we can plug in h equals 0 as we're evaluating this. When you get to the end, you could double check with a graph. So let's go ahead and do that with this of graphing this function. Let's see, the square root. Oops, too many there. Okay, square root of 1 plus x minus 1 over x, and we're looking at 0, and what we can see is there's 1, and that looks like about 1/2 right there. So there's our 1, that's 1/2, and even though it's undefined there, what we did is we adjusted it in a way we're not changing the value, but what we did is we fixed the hole that was showing up there so that we could plug in and evaluate that y coordinate. Okay, let's go ahead with a few more scenarios here. So that one used multiplying by the conjugate with radicals. With this one, so again, I'm looking at that denominator, and if I think about plugging in pi over 2 for cosine, so if I think of my unit circle, pi over 2 is here, that's my coordinate 0, 1. So I'm getting an x coordinate of 0 for the denominator there, which is no good. So we're going to need to make some adjustments. And what I'm seeing is that sine of 2t, I want to look up what is my double angle identity so that I can make a substitution. So the double angle identity for sine lets us change this to, let's see, we're still evaluating the limit as t approaches pi over 2. But instead of writing it as sine of 2t, we can rewrite this as 2 times sine t cosine t, all divided by cosine t. So we've rearranged it using our identity for substitution. Now we can cancel out the cosines so that this is the same thing as evaluating the limit as t approaches pi over 2 of 2 times sine t. And what we can do is just go ahead and evaluate 2 times sine of pi over 2. And sine of pi over 2 is our positive 1, so we're getting a 2 times 1, which is 2. All right, so we may need to bring our trig identities into it and just look them up so that we can make our substitution. And what I'm going to do, just because I know this next one is a big one and we're going to bring in some logarithm properties, I'm going to go ahead and pause there, and then I'll finish up the rest of these.